Hello, welcome everybody. So today we are going to show you one relatively new development that we have been doing, and I hope that you will find it useful. So before getting started, let me check the sound if you can hear me well. Please draw me short notes just to. So you should be seeing the main slide of the presentation as well. So in your question panel, you can enter any note there, and you can enter that. If you can hear me well, please do so to make sure that I can get started. So I don't see any. Nick, can you hear me well?
Loud and clear.
Okay. Okay. Yeah. I see a note now. Okay. Thank you. Perfect. Okay. So, so again, this webinar is it's being recorded, so it will be posted later today, and also on our YouTube channel. The presentation that I'm going to be showing today with you summarizes the development that we have made specifically about modeling the source of oil coming out of pipelines, and that is essentially necessary for risk assessments. And it's based on the result. I mean, it actually is 95% based on user demand. So users have requested that having a tool like this, and we have been adding new features to it, and that's what I'm going to show today. So even though the title says overland spills from pipeline using OilFlow2D, it also applicable to oil on water spills. But the main application that I'm showing is on land. So that's why the title. So again, for those of you who don't know me, my name is Reynaldo Garcia. I'm the director of model development and applications at Hydronia, and I'm showing my webcam so that you can see that this is not a robot or a AI application talking to you, although in a few months or years that will be something difficult to differentiate. So for now, I'm a human, and I'll be presenting this and sharing this information with you. So let me turn off now the webcam so that you can have a smoother ride. So the outline of the presentation includes a short introduction to oil spills from pipeline failure assessments. That's the whole purpose of the tool that I'm going to show you today. I will talk about the challenges of pipeline spill modeling, and then I will talk about the main topic, which is oil pipeline tool that we are showing today. And if you have any questions or comments, you're free to use the question panel on the GoToWebinar screen that you should have. And also you can wait to the end, but I will enter the end for the answers for sure. I would like to thank first and foremost to our clients and users worldwide have been kind enough to trust us on their applications, and some of them are summarized in this screen. Um, so nothing of what we do would be possible without their support, because the funding that we get for development comes from the income that we get from the licenses that these users are using worldwide. So thank all of them and all of you who are already taking advantage of this application. Also, I always thank the partner developers that we have at the University of Zaragoza mainly, and these are long-term partners that allow us to develop new tools, particularly the overland flow, and that is one of the landmarks that integrate with the tool that we are presenting today. Well, in preparing this webinar, I started to search online for pipelines or oil pipelines worldwide. And even though we've been working in this field for a long time, was kind of overwhelmed with the statistics that I could find to share with you. And this map summarizes some of this experience that I got, Googling different topics related to oil pipelines. So what you see is on the screen is a map that shows the main oil pipelines worldwide. And as you can see, they are mostly concentrated on Europe and in the United States, but they are everywhere. And I found kind of contradicting statistics of the length of pipelines worldwide. I found a number of hundred thousands to million of pipeline kilometers. But in either case, depending on what you trust more, it is a tremendous amounts of pipelines that are allowing the transport of crude oil in virtually every country in the planet. So what is that important? Well, because this pipeline can fail, and we need to make sure that these failures will have the minimum consequences on the environment and on the infrastructure that can be affected. And I think by using the tools like the one I'm sharing with you today, we are contributing to minimizing the impact of the potential failure of this pipeline can cause on the environment in general. So this is what you see of pipelines worldwide. If you go to a specific country like United States, which is the country that has the most oil pipelines, we have these maps that includes both gas and crude oil pipelines. And as you can see here, it is staggering the amount of pipelines that cover most of the country. Now, if you can imagine that only a single pipeline like the Trans-Alaskan pipeline here has about 1,000 miles, which is close to 1,600 kilometers. You can imagine the length of pipelines that are available here in the United States. Now, incidents can happen, even though you make all possible measures to avoid them. it is essential to have a way to foresee or predict certain events that could occur in pipeline failures, because these events can occur near sensitive areas that can be greatly affected. So in knowing in advance what could happen, then we can take the actions or planning actions that could be in place at the moment of the events or the incidents that could occur. And then we could, in that case, the measures could minimize what the effects could happen. So that's the importance of the tool I'm sharing with you today. Now, some statistics that were summarized by the USA Pipeline and Hazardous Material Safety Administration, PHMSA. So they have a statistic between 2002 and 2021, and that includes incidents, fatalities, injured persons, and costs caused by the events. And as you can see here, they are pretty stable with an average of 640 incidents, and that includes incidents in the United States only. You have these fatalities, which is also sadly very uniform in time, with an average of 14 fatalities per year. And also the injuries is a quite significant number. If you look at the cost, it's even more dramatic in terms of the amount of money that is lost due to these events, with hundreds of millions to even billions in some years. So these are numbers that make you think of how we can find ways to minimize this damage to the people and to the environment. The causes of the failure of pipelines are varied. I had a meeting with a client a few weeks ago. They are in the process of designing a pipeline, and this is a buried pipeline. It's almost 2 meters below the ground, and they were kind of confident that by the fact that the pipeline is buried, it wouldn't cause significant damage once a failure occur. The thing is that in many cases, even in a failure pipeline, since the failure can occur very rapidly due to a power surge, for instance, that can break the pipeline, and the high pressure from the pipeline can overwhelm the terrain that is confining it, to 2 meters below the ground. So regardless of the state of the pipeline, either if it's surface or subsurface, the spill from it can be catastrophic in many situations. Now, how can a pipeline fail? Well, these are statistics of actual failure of number of failures per cause. And you can see here the equipment failure is one of them. The equipment failure could be a pump failure or a valve failure, for instance, and that the operation of a valve or the erroneous operation of a valve can create a pressure surge in the pipeline that creates pressure way above the resistance of the pipeline, and that can lead to a sudden leak or burst on a pipeline that that can generate a big spill. And this is the biggest cause of failure, as you can see here. Now, corrosion is another one that is the second in percentage cause, and that is a longer term effect, mainly of older pipelines that are out there, and eventually leaks can occur due to corrosion. Then you have other causes, natural force like earthquakes or landslides, or even erosion in rivers. They can erode the bed until it brings up an underground pipeline that crosses the river. Then incorrect operation, excavation damage, and so forth. So there is a variety of causes, but the bottom line here is that any pipeline, even new design pipelines with much better safety procedures in the design can fail, and that's a fact that we cannot overcome. These are some examples of pipeline leaks. This is a surface pipeline. You can see here the effect of the high pressure. So it's a jet actually coming out of the pipeline. Now, from the spill impact point of view, it besides the localized impact here, that of course will depend on how high the pressure is and how far this jet arrives. The amount of oil that gets into the pipeline and the eventual spreading around the area will be the most important factor affecting the area. So if the pipeline burst occur suddenly with a high pressure or lower pressure, it is the actual volume that is out of the pipeline the most important factor. This is another more older pipeline. As you can see, that is older because of the rims that are not used so often now. But see that the failure occurred not at the junction of two segments, but in just in another area here. And this is the Keystone Pipeline incident that occurred about a year and a half ago. That is a buried pipeline, and regardless that it was buried, that you can see the impact, and the spill came into this creek and affected some areas that were relatively far from the spill location. So any of these situations can be typical of pipeline leaks or pipeline spills. Now, the purpose of oil spills on land and water modeling is first and foremost the determination of what would be the affected area caused by crude oil spills. So that's the main purpose of any modeling, and you can integrate the modeling with a risk assessment or other type of assessments for your area, but that will lead to hundreds of applications. But the bottom line is that you need to apply the model to determine what is the affected area for a given event. And by determining the affected area, you need to know where the oil is going and when the oil will arrive. You need to know where it's going to know the extent affected by a given spill, and you need to know when it will arrive to design plans that will take hold once the event occur, and you will have measures, that emergency measures mainly, that will contain the oil as close as possible to the spill location. To determine that and to support that kind of plans, you need to know where and when the oil is going. Now, by applying a model, you consider often what is the affected area, what is in the affected area. So you need to know if it's an urban area, if it's a sensitive ecosystem, it's a critical infrastructure that will be affected. And that is what it's called a downstream analysis. So you make the simulation, you determine the affected areas, you determine when the oil is getting the arrival times of the oil to these affected areas, and then you use that information with the information about the area that is affected to determine how important is to control the spill if the spill occurs in one of these areas. For instance, if the spill occurs in maybe a desertic area that is very far away from urban developments, and you don't have any streams or rivers that could be affected there, or you don't have some ecosystems that are important, then you could say that those areas are not prioritized in order to um, uh, perform planning or some mitigation plans. But if the event occurs in an urban area or a sensitive ecosystem, then you have to put some priority on the planning for those locations. So that's why the use of the model together with the analysis of the land covers or the land use is pretty important as a downstream analysis and assessment. Now, the origin of the spills are varied, but as you can see, they can come from well blowouts or pipelines or tank failures, mostly. And when you're dealing with well blowouts, they are normally dealing from the modeling point of view. We are modeling a few areas to simulate because the wells in the exploitation area are limited. If you are dealing with a storage tank in a port, also the tanks are a few, and you would need to use a few applications in order to assess that risk or that oil spill assessment. But if you're dealing with pipelines, it's a total different story, as we will see now. Now, it's important to, in spills on land, particularly, to consider the dependence of yield stress, viscosity, and density on temperature. There are some oils that show a very sensitive dependence on the temperature, and since the viscosity would increase with decreasing temperature, the final run out distance of a given spill will vary in a big way with different temperatures that with respect to the transport temperature, for instance. So it is very important to consider that in a model that that you want to apply to assess oil spill affected areas. Now, the OilFlow2D model, which is the model that interfaces with the oil pipeline tool that we're showing today, has two main components: the oil spills on land and the oil spills on water. The oil spills on land, as its names imply, simulates the spreading of an oil on the water surface, on the land surface, sorry. And it accounts for the oil properties like density, viscosity, and yield stress. it accounts for the interaction of the fluid with any terrain surface by solving the two-dimensional shallow water equations with a finite volume method that ensures conservation of mass exactly. It also considers heat transfer of the oil with the environment, which is the way to consider the dependency of the oil properties with temperature, and that, as I mentioned, is critical in some oils that have high pour point, for instance. So this model is the oil spills on land, and then we have the oil spills on water, which is a separate model that calculates on one side needs to calculate the river, coastal, and lake hydrodynamics, which is essential to determine the oil trajectories. So once you have calculated the hydrodynamics of the water body, then you use a particle tracking model to determine the oil trajectories. And this particle tracking model that determine the trajectories also determines the changes in oil properties due to the evaporation, emulsification, dissolution, and shore interaction. So the oil, as it's transferred by the water body hydrodynamics, also is changing in time. For instance, evaporation has a very big effect on the oil volume. So a particle that is released, and when we say the particle is an oil parcel that is represented by a particle, has an initial volume, and that initial volume is decreasing in time due to the evaporation of the oil volatile components to the atmosphere. So all of those processes are taken into account with the oil spills on water model. Now, the model has, let's say, two parts: the engine itself that calculates solves the equation and so forth, and then the graphical user interface that is your gate to the modeling. And this graphical user interface is based on the QGIS open source system that has the plugin that we have developed for OilFlow2D, including a preprocessor that allows generating the mesh, adding all of the data corresponding to the terrain, and analyzing different structures that you may have within that terrain, and then it exports the files to run the model. And once the model finalizes running, then you can use the graphical user interface again to generate maps, animations, cross sections, and other type of maps. All of this system is developed with a general objective of being as fast as possible, and for that purpose it has a GPU capability. That means that it can run in parallel mode, taking advantage of graphical processing units that are available in many computers. So if you have an NVIDIA card that is in your computer, probably you can make use of that card to accelerate the performance of the model quite significantly. And you can also install the complete system in a cloud virtual machine like Google Cloud, for instance, and create a virtual machine that will have an NVIDIA Tesla card that will allow the model also to run very quickly. So the heat transfer component, as I said before, allows you to determine the variation of oil temperature as it spreads over the terrain, and also by calculating the temperature, it can determine the variation of density, viscosity, and yield stress in space and time dynamically. And this accounts for wind speed, air temperature, solar radiation that can vary in time during the day and during the night. So it accounts for all the environmental parameters that are critical for to determine the heat transfer. The model allows different options to account for fluid properties dependence on temperature, and it applies to a specific crude oil. So if you have a crude oil that has been analyzed and you have the lab determination of how the viscosity or density change with temperature, then you can use that data directly in the model as well. Now, when you do a simple, I call it simple, or I would call it standalone application of the spill. So you have one spill or one tank failure or one pipeline failure of one point. The typical workflow is very simple. You open QGIS, create a new OilFlow2D project. You load the terrain elevations. With those elevations and an area that defines the model, you generate the mesh. You assign the spill location or locations, if there are a few, define initial conditions, if any, set up run parameters such as oil data, oil properties, and run the model. So once you run the model, you can prepare maps and animations to represent the model results graphically. So it's very straightforward and very easy to follow. So just to summarize this here, step by step, you open the QGIS and with the OilFlow2D plugin, you enter a digital elevation model like it's here shown in gray. You enter a polygon representing the model area. In here, this is an example of modeling an oil storage tank. So it's a single spill location. This storage tank is represented by a weir, and this weir is this open polyline here. There is an initial oil depth within the tank, and then the mesh is generated around the area and takes account of the tank location. As you can see here, there is mesh not only outside the tank but inside the tank. So when we compute this flow spill from the tank, we are computing not only the what's happened outside, but the drain out of the tank itself and the flow within the tank. So as you can see here, the mesh can be refined quite a lot to make sure that it represents correctly the terrain and buildings that are in the area. And then you enter the parameters, environmental parameters that can be on a table, initial temperature of the oil, in this case is higher than the environment temperature. And then you select which model to run and run the model. There is an option to model multiple sources. I will come to that later. So these are examples of the model output. It's an animation of two scenarios. with heat transfer. And here we are using a wind speed of 2 meters per second, and in here is 20 meters per second. So this creates a higher transfer and rapid cooling of the oil. And as the oil cools down, this particular oil has the characteristics of increasing the viscosity very rapidly with the exacerbated heat transfer with the environment. And that causes the oil to stop much closer to the tank than it would have with the lower temperature, where the cooling would be much slower than in the second case. So this is just one simple application that shows a single spill point. Now, what is the problem and challenge of modeling spills from pipelines? Well, the main challenge is that usually assessments of spills from pipelines, and oil pipelines in particular, require running hundreds, if no thousands, of scenarios along the pipeline. That means that instead of having to run a single case, or maybe 2 or 10 spill points, you are dealing with 1 point along the pipeline every 100 meters or 30 meters or even 1,000 meters. So if you imagine the example I mentioned before of the Alaskan Trans-Alaskan pipeline that has 15 or 1,600 kilometers. So even with one spill every kilometer, you're talking about 1,600 scenarios, 1,600 spill points. In reality, this particular pipeline requires about 50,000 spill points. Now, performing this one by one is totally impractical or impossible, I would say. It would take years to perform that kind of analysis one by one. So that's a big challenge to address. So at each of these spill locations, you need to calculate the potential spill volumes or flow rates and outflow hydrograph for each spill. So imagine that because we are dealing here with a prediction. So this is a spill that hasn't occurred. So we are trying to plan for mitigating potential spills or assessing the risk of affecting different areas. So since we don't know initially where the spill is, we need to have scenarios for spills at any location along the pipeline. And for each one of them, we have to assume that there is a spill, and then we need to calculate the volume or flow rate that came out of that. So we need to analyze the pipeline hydraulically in order to compute that process. Once the oil is overland, then we need to compute the spreading of that oil on the land, and the flow paths are rarely 1D. And that is important because sometimes, if you use an oversimplified approach, assuming that every stream is one-dimensional, you are ignoring some important characteristics of the rivers that are not 1D and are two-dimensional. So by using a 1D, you may be oversimplifying the assessment you're doing. Also, the flow, the spreading of this overland, of this fluid overland, it needs to account for the free surface of the fluid itself, but also that it's a viscous flow. It's not water flow, although water obviously has a viscosity, but usually the crude oils have a viscosity much larger than water, and also has a viscosity that can change in time. So many oils are non-Newtonian, unlike water that is a Newtonian fluid. Many oils are non-Newtonian. So considering the non-Newtonian uh, characteristics of the oil is critical. Also, oil properties can change in time during the spill. Density, viscosity, and yield stress can change to a level that can affect the run-out distances from the spill location. Now, a big challenge also is that each spill simulation generates a lot of results that need to be processed, because you have a numeric values, and with a bunch of files with numbers are very difficult to process and analyze. So you need to create maps, and this map creation, since you are dealing with so many spill locations, needs to be automated as well. Now, I told you at the beginning that what we do mostly respond to requests from our own users and clients, and some other requests that we get from time to time. And this is one of them. This was an actual email that was sent of an older version of the model, maybe before 2021. And they were trying to use the model to simulate a pipeline. And they sent us an email highlighting the difficulties they had in applying that version of the OilFlow2D model that didn't have an oil pipeline tool like the one we have today. So they said, well, first they were talking about the lack of automation, and the analyst, so that means the modeler, can do a batch run for many leak points. There was a tool that was available at that time, but the program does not automatically generate the overland spill plumes. Instead, it generates intermediate results from which plumes can be generated. To generate the plumes, the analyst must manually perform a series of post-processing actions on the intermediate results for every leak point. Quite a lot of clicks are involved per leak point, and it's the same sequence of leaks for every leak point. It is time consuming. If the data changes and a new run is made, the analyst must perform the manual post-processing all over again. So imagine what is the problem that that this user had. So they had a model that could simulate overland spill, but it was quick in solving one spill, but then the actions that needed to be performed by the modeler in order to generate hundreds of spills was completely overwhelming to them, and that's totally impractical. So this development that we are showing today addresses this particular limitation that we had in 2021 and until, I would say, early this year. So the oil pipeline module is a response to that need that we were confronted with. So the oil pipeline module, it's called the OP for OilFlow2D, allows automating the simulation of hundreds or thousands of leaks from pipelines that are often required in pipeline integrity assessment. So that's the main purpose of the oil pipeline module. It can be integrated with overland and oil spills on water. Both models can be integrated with the oil pipeline modules. That means that by using the oil pipeline, you can generate oil sources that can eventually be used for the overland or for the oil on water model. By the way, you can use the oil pipeline on its own. So if you don't have OilFlow2D and you have the oil pipeline module, you can use the oil pipeline module to apply to determine the outflow from the pipeline. Now, the oil pipeline module has two parts, I would say, the pre-processing and the post-processing. What I call the pre-processing includes actually the calculation part, but it mainly allows entering a pipeline, polyline, and multiple spill points. So you can enter one pipeline, or you can enter multiple spill points, but the most use would have it will be the from a pipeline. So using a pipeline that you can have on a shapefile, or you can enter directly in the model, the pre-processing can automatically create the sources layer for batch processing of the overland spill. It can compute the steady state initial pressure distribution along the pipeline, given the oil flow rate and pressure head at one point. It can consider the closing time of block valves that can be inserted in the pipeline or can be already there. It calculates the output flow rates from the leaks that can be of any diameter, and it calculates that in two stages. First stage is the period between the initial time and the time of the valve closing. So the user says, let's say, valve close in 1 minute. So between time 0 and 1 minute, there is an initial stage. And from 1 minute to the drain out, complete drain out of the pipeline is another stage. The pipeline polyline can contain elevations, or you can just enter a two-dimensional pipeline and the program can assign the elevations from the digital terrain or digital elevation model. So you have that option as well. Now, once you have that, you are ready with the pre-processing. You're ready to simulate your overland or oil and water, and based on the model results of this oil spreading that occurs in batch mode. So that means that the oil will compute the 1,000 or 2,000 or 100 spills in batch mode. So it requires no user interaction. Once you give the data, the spills will occur for each of the spill locations, and you don't have to be in the computer. So you can leave that overnight, and or leave it for an hour or whatever time it takes, and then you will need to just look at the results afterwards. Let's see. Give me a second here that I got the. Okay. So specifics of the oil pipeline tool includes the oil pipeline layer. It's a new layer that is this one here that can be used to enter a pipeline. Then there is a new valves layer that is used to enter valves or block valves that can be along the pipeline. There is the new oil discharge calculation tool that will, in addition to determine the flow rates out of each of the spill location, it will automatically create the sources layer with the associated hydrograph, spill hydrograph, that will be ready to compute the overland flow. So that is all included as tools within the oil pipeline tool. And then the post-processing as tools to automate the map creation, which is was another source of difficulty or limitation in the previous versions. Now the workflow for an oil pipeline application is as follows. You open QGIS, you create a new OilFlow2D project, you load the terrain elevations, you create an empty oil pipeline and valves layer, you enter the pipe polyline, you enter the valve location if any, and you run the program to calculate discharge versus time for each spill. And that will generate the sources layer. So that is the typical workflow that you would follow to apply the oil pipeline module. Now, this is an example that I did from scratch for the webinar based on the fact that we have many applications that our users share with us for support purposes, where we are not allowed to share those with you due to the sensitive information that they contain. So what I did was to create one hypothetical case using public data exclusively. And so I needed a terrain elevation. So I went to the USGS website that has a very good terrain information, even based on LiDAR in many places, in most of the United States, I would say. So I went ahead on this site, and this is the south of the city of Seattle in Washington State in the United States. And I picked this location because it has a terrain that is kind of peculiar. And also there is a port down here that is the Tacoma port. But again, everything here is public information, and it's in some of them is just for illustration purposes, as you will see. So this is the terrain that I enter. It's a high resolution terrain. It's about 1 meter resolution. And then I enter the pipeline. Show it to you. Well, I will show it to you later because I have the QGIS project open, but the pipeline runs around this area. I will show you in this demonstration how it's centered. But there is a pipeline. I mean, again, it's a hypothetical pipeline coming here, and then based on that location, I run the oil pipeline break model and enter the data. So this is the data that you will need for applying the oil pipeline model. The calculation interval, that's typically very small. You can enter small value here, 1 second or less. If you want, you will see it's very quick. The distance between spill points, in this case, 100 meters. The leak diameter. Now, the leak diameter should be a little smaller. The maximum should be a little smaller than the pipe diameter. The pipe diameter here is 0.3 meters. So I selected 0.29 as leak diameter. This is the discharge coefficient. This is a discharge coefficient for the orifice corresponding to the leak. The friction coefficient within the pipeline. The density of the crude oil, the kinematic viscosity, whether to use the basic of heat transfer model. This can be changed afterwards. It doesn't matter. I mean, it can change in the data input program after. The initial pressure head at the pipe end, the initial flow rate on the pipeline is 0.1 cubic meter per second, 100 liters per second. The valve closing time, I'm not using valves in this example, so it's 0. But if you had valves, well, there are valves are downstream and I mean the extreme upstream and downstream, but they will close instantaneously at the initial, or not instantaneously, but very, very close to the initial stages. The elevations to the spill points are obtained with a DM layer, not Google Earth. This is this one that was available, but this was not the one I used. The one I used to generate the elevations on the pipeline are the ones from the DEM, the USGS DEM. And then you run here, you click run, and then the model runs and generates this here. So it generates the, in this case, 201 spill locations along the pipeline. This is a zoom in of this sector here. So each of these spill locations has a corresponding outflow discharge as a function of time. And all of this is in the format of the that is required for the OilFlow2D model to run. So you get all of the details of the files already created, ready to run once you perform that computation here. This is another detail of the spill locations. The green line represents the pipeline. Again, this is not a real pipeline, it's just for illustration purposes. Now, the oil leak discharge calculation is summarized in this slide. So you have first the computation of the initial steady state, and this line indicates the total energy line, and this is the pipeline profile. So this is the pressure head plus the velocity head along the pipeline. So this is calculated first by the model, so that this is the initial hydraulic state of the pipeline. Then it is assumed that the pipeline is completely filled, as in this schematic that you see here. Now, for each spill point, that is the rupture point represented with the R here, there is a iterative process that starts to compute the unsteady 1D or quasi unsteady 1D continuity and energy equation along each of these reaches, from upstream to the rupture point and from downstream to the rupture point. So they will be drained down from both sides, because after the initial stage, the pipeline has an initial condition, but then the flow rate stops. The pipeline starts to depressurize and starts to drain out of the pipeline the oil from here. Now, the flow will occur not only from the highest points, because they could be, you know, and the initial flow rate can overcome these high stages, but eventually the drain of the pipeline is not complete. At the end, there may be remaining oil in the pipeline due to the dynamics between inside the pipeline. But at each time step, the model computes the discharge based on the flow from each side of the pipeline. Now, at the end, you get a table for each spill point, that is the time versus discharge. For, as you see here, this is a table that is one of the outputs. For each spill point, you get the discharge and for each time. So this is an automatic process that computes that. And again, if you had valves here, it will consider the valves and the valve closing time. So at some point, you may want to test how effective are the valve locations to minimize the flow rate out of the pipe, or the volume out of the pipe. This is an output from one of the spill locations, the discharge versus time. And you can see it can be complex because of the particular profile of the pipeline and the location of the rupture point. There are a variety of files that are generated in the model with numeric values. First, you have an integrated hydrograph table that will give for each of in this case, we have like 200 spill locations. We get the discharge over time. And this we had imported in Excel just to visualize the results. So this includes all of the sources. Interestingly, if you look at the numeric values, and these are minimized here to just visualize these forms here. So these are the times. So you see the time is in vertical. The time is increasing in the vertical. So you see here, this location, it's maybe it's a high point, and it drained down very quickly. And these locations are in lower points, it drain down slowly. And if you compare this area here, this reach, with the profile, it looks very similar. I mean, the high points correspond to spill locations that drain down more rapidly, and the lower areas are points show drain down much lower. So that's interesting to see that they represent, they correspond to the profile, which has a big importance in how fast the pipeline will drain. So you have other numeric outputs like oil spill volumes per each spill location, upstream and downstream, before and after closing. So you have here this table, the spill point, how much volume was a spill in total from that spill point upstream before the valve were closed, and after the valves close. In this case, we have a 0 time, so that's why we have 0 volume before the valves close. So everything is after the valves close. And here you see you can see the totals and also the specific spills, either from downstream to upstream. You have also the here you have the energy line. So you have for each spill, the spill location, the elevation of that location, the distance upstream, and the total energy line values here. And this allows you to create this plot that I showed you before. Now, once the spills are generated and the sources are generated, you can directly run the oil flow model, and that will run automatically in batch mode. So you can enter the that run process, and it will run all of the spills without any further interaction of the user. So you will see them on screen, but they will occur it will tell you which one. You can see here, this is a spill 40, 41, 42, 43, and you will see that this advances in time automatically until it completes it completes the simulation for the 200 or whatever number of spills you have. Now, the model will write the results for each spill in separate directories. So they are not mixing of results here. So you will have, at the end, you will have each directory containing the total results for each particular spill. And also you can use the scenarios and mix with that. So you can have one scenario for one situation, another scenario for one situation, and within each scenario, you will have each of the spill locations in separate subfolders. So the second part of our automation that we added is the generation of maps and shapefiles. So in the past, we needed to go to each of the desired map that the user had to output and go one by one. So imagine the overwhelming task of going for each of the spill locations. You have to open the dialog, select the plot you wanted, click OK, wait until that happens, go to the next one, and then so it was very time consuming, as the email from the user you saw before was explaining. Now we have several options. You can in here, let's say if you select the maximum depth or the maximum flood area, you can select the option for single map with source spill selected. That means that it will just plot the one that was selected, let's say spill 83 or whatever you selected. Or you can select the maps for all of the spills. That means that you will select, if you select that, the program will create all of the spills in separate folders, in separate shapefiles. So you have one shapefile and one map for each spill. Or, this is very useful, you have the integrated layer that contains all of the spills. So in a single layer, you have all of the spills, and then you can click on and off each one of them if you want, or you can't export them because they are identified. So you have the information about all of the spills in the same layer. This is an example. The previous one is this one is the depth, and these are the spill area, the affected area. As you can see here in this example, each is colored within a specific area here. And this is an example also of another site with a spill and for only one site. So you have the depth for only one location and time. But as you can see here, turn off, you have the spills for this particular time for all of the spills for this scenario. Okay, so let me show you the very quickly. I will give you show you an example here of how I set up that model. So what I did was to create a new project. I only used a few of the layers. I didn't use all of the layers here. So what I did was to create an empty project with, let's say, in this resolution, it changed the So I'm not using this one here. So I will create this with empty. So I'm not creating any, I'm not using any of these layers here, but I will use the project direct, the projection for this particular site is the 2855. So this is the location which I need to enter. The name of the scenario, I will leave it as space, and I will use here the Tacoma folder, which is an empty folder that I have there. Okay, so this will create for you an empty project, and then I will add the raster that represents the terrain. So I have it here within the Tacoma site. This is the raster that was obtained from the USGS site. Is here. So you can see it's the same that I used before. I will add the Google Earth map. So this is the site, and then I what I did was to add the so I added the layer that corresponds to the oil pipeline. Okay, so I added this layer, and in this layer I enter a polyline, which is this one. Approximately the one I enter is something like this. And then when I right click, it says the pipeline ID, it says 1, it doesn't matter, say call pipe 2. The pipe diameter, I enter 0.3, pipe roughness, that's okay, click OK. And then, so this pipeline, this, let me bring down this. So you see the pipeline traverses some irregular terrain. Now I have everything ready to run the oil pipeline break model. So the data that I will use, or I used before, I will repeat it here, is the time step is 1. Let me put here 200 meters, not 100, so you see the difference. Leak diameter 0.29, discharge coefficient 0.44. Density, I will leave these values the same. The output oil temperature, you can change that later as well. So I had here, this is the pressure head at the end of the pipeline. You need to know that I'm using 80 meters just for this example. The initial flow rate is 0.01. So it's 100 liters per second. Closing the valves at time 0. The dam layer is going to be used to assign the spill points, the elevation. And I'm using here the one that is the dam merge. Then I have everything to run. There is an offset. This offset, it's if for some reason the elevation of the pipeline is above the surface, and then it will displace it upstream, up and down the amount you give here. I will leave it 0. So now it's computed. So now you see it automatically created the spill locations, but more importantly, it created a source layer, which is this one that is shown here. So this is the source layer with how many sources created? It should be 95 points. You can see here in the attribute table that each point has a discharge versus time condition, and that it has the file associated with each source point. And if you go to the folder, the model hasn't run. I mean, the overland flow hasn't run. This is just the pipeline. So you will see here you have the oil graphs. This is the table I showed you before, that you have the times and discharges that you have for all of the spills. You can directly import this in Excel, and you have for each individual spill, you have the flow rate. You can see here that you have the flow rate, the number of values in the file, the time, the flow rate, and the temperature, because I selected 35 degrees as outflow temperature for the heat transfer model, which is a constant temperature here. So this is the outflow hydrograph from this particular location. And then we have also the energy line. So this is another outflow output file. We have the oil pipeline reaches. I'm confused because it opens in the other folder, in the other monitor. This is the file that tells you for each spill the elevation, distance along the pipeline, volumes up and down, etc. So now we would be ready to process to create the mesh and the actual simulation. So I have that already done with the previous examples that I show you. Is here. It will take a few minutes. It takes to perform this 200 point simulation. It took about approximately 10-15 minutes, maybe 20 minutes. And at the end, you are able to, as you can see here, to automate the mapping process as well. So if you want to make a plot, you select the maximum result maps or individual maps, and you will see here that you select for any of them, and then you can select which variable you want and select a single map or the integrated value. And once it's done, it processes the individual maps and the integrated value if selected, and then you have it here. So you have here the so you see this is the one for spill number 2. Spill number 1 is this one little here, and then you have also the integrated depth or the frontal way arrival times as well. So you have all of this information or maps created very quickly, because you don't have to go as in the past one by one. So you go and you process them simultaneously. So yeah, so that's what summarizes the oil pipeline model. So if you have any questions, I'll be happy to answer them now. Okay, let me see. See, I have a few questions here. Well, I apologize because I didn't see the messages that you were sending me about the initial screen that were showing the ones with the uh, not the one that uses the whole screen, but I it's halfway in the presentation I saw it. Okay, so let me. I have Ryan is asking, in generating the hydrograph of each release location, the valve are accounted for, but is the period of active flow prior to pumps stopping also included? Yes, yes, yes. It accounts for. It's two stages: the period before the valves closing, and before pumps stopping, and after that. So yeah, it accounts for that process as well. Um, Is the hydrograph included in the attribute data for each release location feature? Yes. Yes, the file is one of the attributes. Did the run oil break model take into account in consideration valve location, time to close the valve, etc.? I didn't see you upload valve location to the Tokomo example. No, I didn't use that. If you wanted to do that, then you load um, there is a layer that is called uh, this will it's called now the OPL boundary condition layer, but it will change to valve location, but it's the same layer. And then it's a point layer, as you can see here, and then you can enter a valve location, whatever in the pipeline, and then let's say you can enter here valve 2 or something. Then this valve location, you can have as many as you want along the pipeline. And then when you enter the closing time, those valves will close. Now there is a limitation now that it's assumed that the valves will close at the same time. So if you have 10 valves along the reach, the 10 valves will close at the given time. So there are no specific time closing for each specific valve. I have a question here. Julio is asking about the infiltration. Yes, the model can compute infiltration loss from the overland spill. That's an option in the OilFlow2D model. Yes. I have a question here. How does the solution deal with tile dam data? Well, the present we account for tile dam data in the model itself. In the example that I use a merge data, a merge DM. I'm almost sure, but not 100% that It can include multiple DEMs, but I will need to go back to you because I know that that was discussed during the development meetings, but and it's on. If it's not developed, it will be very shortly because that's something that we have discussed. I'm not sure if it's in this version it's available, but it's going to be available for sure. Can check valves preventing backflow only be included? Not now. Again, the valves are very simple. So in this version, it's only including, I mean, it assumes that they close. So they do not allow any flow across them whatsoever. They are not check valves. They are just, standard close valves. Um, um, okay, I have a question of Julio is asking about the availability of the module. The module is distributed separately or optionally. I mean, the way it works now, you can purchase it independently. I mean, you don't even need OilFlow2D to use the OP. You can get it independently, or you can get it as an add-on to the OilFlow2D model, but it's separate. It's separate. It's not included in any of the previous models. It's a separate module. There you can consult the website, and you have more information if you go to our website, www.hydronia.com/oil dash pipeline. You will see the information about the more details and also the distribution and so forth. Okay, I have another question here. Will you be performing a webinar showing how easy it is to take overland spill results and adding the results to the overwater model? Once both are done, it is easy to merge the results into one map or project. Well, presently, the overland and on water models are working separately. So you have to extract the results from one, the overland, and put it into the other. There are two things that we are doing now, two developments. One development is related to the integrated overland and on-water model. This overland and on-water model will take into account a water flow in a riverine water body, and in a seamless way, it will compute the overland flow over solid terrain and determine the spreading on the water surface. This is under testing at this point, so we don't know dates yet. If everything works well, which we still don't know. I mean, how the model is eventually developed. The model is developed. We are testing how it works, the stability of the numerical schemes and so forth with the developers of in Spain. But as soon as we get that tested, we'll have that. I mean, if it works well, it will be available, and this will be certainly a very interesting addition to what we have now. That's one thing. And the other thing we're doing for the existing oil and water model is the automatic extraction of um, the oil on land model to the oil on water model. So that means that once the spill hits a water body or intersects a stream, it will generate all the files necessary to run the oil and water model for that. So that's also under development, but it's not available now. Well, okay, so I guess I went a little overboard in the time. I apologize for that, but I had a lot of things to share with you. I hope you find that interesting. If you have further questions, feel free to email me, and we can continue discussion later on. So thank you very much for your time and interest. I look forward to continue collaborating with you. Thank you very much.